In this online lecture, what we're going to do is we're going to talk about our first reaction. Our first reaction is going to be the addition of a hydrochloric acid. X is a halogen, so fluorine, chlorine, bromine, or iodine. The ones that we really use are hydrochloric acid and hydrobromic acid. But the addition of hydrogen halides to an alkene. So if we were going to add them to an alkene, what we would find is the simplest way of looking at this is if we put the hydrogen halide above the double bond or below, it doesn't matter, adjacent to it, lined up like this. What will happen is this bond will break and this bond will break, and we get this bond forming and this bond forming. Notice there's a conservation of bonds. Okay, because there's conservation of electrons, and the bonds are electrons. When they add, what happens is the hydrogen ends up being attached to one carbon and the halogen to the other, and we call the product an organohalide. The halogen ends up on the more substituted carbon, and this is called Markovnikov addition. Now, we're going to go into this in much greater detail. One thing you need to know is that this is not the mechanism what I'm showing you. The mechanism is what I'm going to show you next. This is just showing you what is the net overall reaction. The mechanism of this addition is very simple, but we still have to look at how it occurs. And remember, we're using arrows to indicate the movement of electrons. This is called electrophilic addition because the proton, which is the electrophile in hydrogen bromide, adds first to the alkene. So let's look and see how this happens. If I look at the first arrow, what we show is the electrons in the pi bond reaching out to grab the proton. Because hydrogen cannot have two bonds, the electrons in this bond jump onto the bromine to make bromide. This is going to put the positive charge on one of the carbons. That one carbon then now is an electrophile and the bromide is a nucleophile. So the bromide jumps in with its electrons. It has a non-bonding pair that it reaches out and grabs that carbon and forms a bond. These were the electrons that were in the non-bonding pair. Okay, and so you can see on one side, notice the hydrogen was added here. And so now you have two hydrogens, and then the bromines added to the other carbon. So what happens in this is that the halogen ends up attached to the more highly substituted carbon. This means more highly substituted carbon. That means the carbon with more carbons attached. This is called Markovnikov addition, to have the halogen attached to the more highly substituted carbon. Why does this occur? It's because when the proton does its electrophilic addition, a carbocation forms. And the more stable carbocation has a lower energy. This intermediate determines, the energy of this intermediate determines the height of the transition state before getting there. So the carbocation that has the greatest stability is fastest formed. So if I look at the stability of carbocations, what you would find is the carbon that has 3 carbons attached when it's a carbocation is the most stable. Next, where there's 2 carbons attached to the carbon, then 1 carbon attached, and then the least stable of all is going to be a methyl carbocation. And we call this a tertiary carbocation, a secondary carbocation, and a primary carbocation. Methyl is considered primary also, but it's less stable than the primary carbocation that has a carbon attached. This occurs because just as with substitution on a double bond, the electrons that are in an alkyl group attached to a carbocation can overlap with this orbital. This orbital is basically an empty orbital that's very hungry for electrons. A carbocation will have a carbon that is sp2 hybridized, so these orbitals right here are sp2 orbitals. And then there's a leftover p, and that leftover p is empty. That's why there's a positive charge on the carbon. That empty p orbital overlaps with electrons that are in a carbon to either hydrogen or a carbon-carbon bond that is parallel and adjacent to it. That stabilizes it. So the more carbons that are attached here, the more possibility for this kind of overlap, and therefore greater stability. So how do you determine what is the outcome of a reaction? Because there's two possibilities of the hydrogen and the bromine adding to an alkene. The hydrogen can add to one side or to the other. So what you do is you test it out. You test to see if I add hydrogen to this one, what carbocation forms, and if I add hydrogen to that one, what carbocation forms. Then you choose the one that gives a more stable carbocation and put the halide on it. Here's an example. Do you see how this carbon is different from this one? This carbon has two carbons attached over here, and this one has only one. If we add the hydrogen chloride to this double bond, the hydrogen can go either here or here. If it goes here, then the carbocation will be on this carbon. If it goes here, then the carbocation will be on this carbon. Because this carbon has 1, 2, 3 carbons attached, and this one has only 1, 2 carbons attached. This is a tertiary carbocation and is more stable than this one. Therefore, the chloride ends up attached to the carbon that has more carbons attached right here. So now that you understand what controls this kind of reaction, go ahead and figure out what are the outcomes of these reactions. Okay, if I look at this reaction, I can have either hydrogen add here or here. If I add hydrogen add here, it would put the positive charge here. If I have the hydrogen add here, it puts the positive charge here. This is the more stable carbocation, so that puts the bromine on that atom, and this is the result of that reaction. If I look at this alkene, I can see that this carbon could have the hydrogen atom added and it would put the positive charge on this carbon, or the proton could add to this carbon and put the positive charge on the carbon here. If it adds to this carbon, that putting the positive charge here, that would form a primary carbocation. With the positive charge here, that's a secondary carbocation, which is more stable. So the product ends up with the chlorine added to this carbon right there. What alkenes could have produced this? Well, if I look at this halide, this is 2-chlorobutane, it had to have come from an alkene. What alkene? Well, the double bond either could be here or it could have been here. Let's look at the possibilities. It could have been from here, where a hydrogen had been added here and the chlorine here, or it could have been added where a hydrogen was added here and a chlorine here. So the double bond could have been here or it could have been here, either of these possibilities. Now, if I go and I add a hydrogen to this carbon, you would put a positive charge there, which gives you this. If I put a hydrogen here, that would put the chlorine over here. Those two compounds are exactly the same, so this would work. But this one would also work because if I put a hydrogen anywhere, it's going to go here so that the positive charge is on this carbon. The hydrogen would not add here and put a charge there. So both of these alkenes would produce this. Now if I look at this compound, which alkene would be needed to produce this? Again, you consider both possibilities, that the double bond used to be here or the double bond used to be here. Well, let's look at the double bond being here first. If this were the compound, when you put a proton on, the proton would go here and the bromine would go here. So it can't produce this compound. Let's look at this possibility where the double bond had been here. If the double bond had been here, then a hydrogen could go here and a bromine here, and that could form. But the problem is, if I put a hydrogen here, a bromine would go there, and both of those are equal stability. So if I did this reaction, I would get a mixture of both the bromine here and the bromine there. So it wouldn't be a good reaction overall at all. If I look at this compound down here, what alkene would form this? Well, I could have a double bond here and a double bond here. Would that work? I wouldn't want to have the double bonds on the inside because then the chlorines could end up on either side. If I have them here or here, when I add a proton, the proton would add here and the chlorine there, and a proton could add here and a chlorine there. So this would be what you'd want to select to make this compound. This mechanism occurs in two steps. And what we're going to do is we're going to take 2-methylpropene and we're going to look at how this mechanism occurs and what changes in energy occur. So here is 2-methylpropene and hydrobromic acid. When the hydrobromic acid or hydrogen bromide adds to the compound, what happens? It adds to this carbon so that a carbocation forms here. So that's shown here at this energy. It's very high energy. This is an intermediate. It is not stable. It's ephemeral and lasts only for a brief time. Very brief time. But to get there, it has to go through a transition state. So the transition state goes up and over. Now, once this forms, there's such a small activation energy for the next step that it stays only a brief moment and then whoo, goes over here and the bromide adds to the carbocation. You can see this is an exothermic reaction, so heat is evolved. The rate limiting step is right here where there's such a huge activation energy because the proton adds to this to make a high energy state. This takes a good bit of energy for the proton to add. So that is a slow and rate limiting step. When we have this reaction, we can have it happen with hydrochloric acid, hydroiodic acid, and hydrobromic acid. The hydroiodic acid, we don't buy bottles of that. What we do is we generate it in situ by mixing potassium iodide and phosphoric acid. No big deal. But you will sometimes see this instead of HI. Now, if I look at 2-methylpropene, you're going to see you get the same kind of result as if you used hydrogen bromide instead of, hydrogen chloride instead of hydrogen bromide. The proton adds here, the chlorine adds here, and you get a more highly substituted halogen. If I look at this compound, you would have exactly the same result. The proton would add here, and then the iodine would add here. Both of these are Markovnikov addition. Remember Markovnikov's rule. If the alkene is unsymmetrical, the hydrogen halide can add two different ways. The way that's favored is to put the halogen on the more substituted carbon. We say that the reaction is regioselective, meaning that it only goes one way. And this is called Markovnikov's rule, or we call it Markovnikov addition. One thing I want to point out to you, if the double bond has the same type of substitution on either side. Notice down here at 2-pentene, the ethyl is different from the methyl, but it's still only one alkyl group on that carbon and one alkyl group on this one. So there's really no difference in the stability of the carbocations that form. So there's no selectivity in this reaction. We get two products that form, and so we say it's not regioselective. There's no difference in the stability of the intermediates, so both products are formed essentially in equal amounts. Go ahead and try this product. Order these carbocations by stability, remembering what do you consider, and then order them. If I look at these, you can see that we can recognize this is primary, this is tertiary, this is secondary, and this is secondary. So because of that, this one will be most stable and is given a rating of 1. These two have about the same stability, and so they're 2, and then this one is primary, so it's the least stable of them all. Let's look at something called Hammond's Postulate. Hammond's postulate is that the transition state energy, or the structure of the transition state, is similar to whatever it is closer to an energy. So if I look at this alkene and I look at the intermediates that form either this one, primary, or this one, tertiary, for the two possible reactions, this one is higher in energy. So Hammond's postulate says that the transition state, which is closer in energy to the carbocation than to the reagent, is going to be higher in energy. Because this one's more stable, the transition state will also be lower then, because the energy of the transition state is closer to whatever it's closer in energy to. Do you see? This is closer in energy to the top than this way far away. So the transition state is closer in energy to this, and so the structure of it is closer in energy to this. It's one of Hammond's postulates. What this allows us to say is because this is less stable and this is more stable, the more stable intermediate actually has a lower activation energy than the less stable intermediate. So by looking at the carbocation intermediate, we can infer which one will be the faster reaction. And this actually seems to hold for us quite well. A major problem with carbocation intermediate reactions is carbocations are not terribly stable. So if they're not stable, they're going to try and rearrange to stabilize themselves. When you have a rearrangement, you can have two possibilities. So let's look and see what kind of rearrangement we're talking about. If I look at this compound, when I add a hydrogen to this, or a proton, it adds right here, and that puts a carbocation here. What happens is, because a secondary carbocation is not as stable as a tertiary carbocation, this hydrogen, the electrons in this carbon-hydrogen bond, can actually walk over to here and leave a positive charge right here. So when this reaction occurs, we get it where the chlorine actually is added here, but then at the same time, this hydrogen has time to walk over and produce a carbocation on this carbon, and we actually get this one too. Because it is a hydrogen that shifts over to change the carbocation structure, we call it a hydride shift. Hydride is hydrogen with a negative charge. And so basically the electrons and the hydrogen walk over together. And so we call it a hydride shift, hydrogen with electrons. So here's an example of how it occurs. The electrons reach out and grab this proton, and then it makes a chloride by electrons jumping onto the chloride. This carbocation has a chance to react, and it does, and make some of this by the chloride adding here. But sometimes before the chloride adds, this hydrogen walks over and gives you a proton right here. That then reacts with the chloride. Once this forms, it doesn't go back. Why? This is more stable than this. Why does this go this way at all? Because you increase the stability of the carbocation if the hydrogen shifts over. Now, do you always have carbocation rearrangements? No. And for the most part, I'm going to give you compounds in which you won't have carbocation rearrangements. But they do occasionally occur. And the kind of problems that I will give you is where you look and you say, oh, a carbocation rearrangement must have occurred because the carbon structure changed. So if you don't have a tertiary carbocation, the rearrangements are possible. They do confuse the situation. So how do you figure out what happened? Draw the carbocation that you think should have formed, and then look to see what would have walked over. Because not only can you have hydrogens walk over, but you also can have alkyl groups walk over. They're called alkyl shifts. So here is a hydride shift, the hydrogen and its electrons walking over, and noticing it's putting its charge over here. Or you can have an alkyl shift where the alkyl group walks over, and notice that the positive charge changes to the other carbon. Both of these are possible. This reaction occurs. So what I want you to do is see if you can figure out the mechanism for its occurring. Do it by going stepwise, adding your proton first, figuring out what carbocation forms, and then seeing what kind of shift can occur. Okay, if this compound adds a proton, one place the proton can add is to add here. Okay, if it does, this is how it would do it. The electrons here would reach out and grab the protons, and then the electrons here jump on there. So that could put the hydrogen here. It could add here, but that won't give us the product over there. We'll have it add here. That gives this carbocation. Once that carbocation forms, one of these alkyl groups can walk over, like that. If that alkyl group walks over, what do you get? You get the carbocation here. Now, the bromide can dive in onto that carbocation, and then it forms this. And that would be the mechanism for that reaction.